for NEET is now available on the Google Play Store. Try it out for free.
Hello students, so we have started to understand few important concepts of organic chemistry. So many things we have understood like fission of the covalent bonds, homolytic, heterolytic cleavage we have understood in details, quite a detail, and then we have also seen what kind of different chemical species which are formed because of the heterolytic and homolytic cleavage and their stability, order of stability we have also understood. Then we show the nucleophilicity and electrophilicity in some important terms like substrate and reagent, what is a substrate and how one can recognize which species in an organic reaction can be considered as a substrate and which one is considered as a reagent. So these things we have already understood and the nucleophiles and electrophiles and the nucleophilicity and electrophilicity order we have already seen. Now we are today's lecture will be studying electron movement in organic reactions. And with the electron movement, this electron movement in an organic reactions can be a permanent movement or in a molecule, or maybe this can be a temporary effect during a chemical process. So what do we see even in an organic molecule? Because of the difference in electronegativity, we see the shifting of the electron density or a shared pair of electrons towards a certain atom. And so that shifting, that movement, that displacement of electron is called the permanent displacement or the movement of electron. However, we also see because of the presence of certain chemical species or the reagent or the chemical in the certain chemical environment, we also see some kind of movement is facilitated by the presence of these reagents, and uh, those effects are only valid and those effects are only effective when these reagents are available. Once you remove these reagents, those effects they vanishes, and so what do we see? Those effects are temporary effects. So let us now understand the electron movement in organic reactions and how the electron movement one can show with a curved arrow we have already seen in the heterolytic cleavage and also with the half arrow in the homolytic cleavage, the hook arrow, half hook. So the fish hook that you understand. So half-headed arrow. And so the movement of electrons in organic reactions can be shown by curved arrow notation. It shows how changes in bonding occurs due to electronic redistribution during the reaction. To show the change in position of a pair of electrons, a curved arrow starts from the point from where an electron pair is shifted and ends at a location where the pair of electrons will move. These things we have already seen earlier. Now we can see this kind of movement can be of three types. One in organic reactions, and this kind of arrow movement you should understand because while understanding the reaction mechanism or the showing the reaction mechanism, arrow movement is very important. So what we can see is the double bond is in an the single bonds are an alternative position and they are alternate. So what one can see this double bond may shift to this place and the single bond and this bond will become the single bond and this one bond then will become a double bond. So what happens if this carbon atom, if there is a carbon atom here, if this carbon atom is having an empty p orbital, or any atom which is here is having empty p orbital and this half filled orbital and half p orbital, if it is also having half filled or even empty. So what can happen to this p orbital now the pi bond can be formed between this atom and this atom, and so this bond will be delocalized, it will move to this place. And so this is what is the movement of bond or the delocalization of the bond. Ideally, one should show a negative charge in this is at this place and a positive charge here. But since we are here, our focus is mostly on to show how an electron or the shared pair of electrons may move in an organic molecule. The really the but the accuracy of this kind of representation is not the focus here. We will see when we will see this kind of with movement with accuracy when we will see the resonance or the mesomeric structure. And what I have said that in this structure, this there should be a positive charge here and there should be a negative charge ideally. This is because although we have not shown, I have not shown it here, because if this shared pair of electrons and the entire two electrons will move to this side, so one electron which was shared from this carbon atom, that electron has also moved to this place. And if that electron has also moved to this place, so this carbon has lost its electron. And this carbon, this Y electron, this Y atom has its electron, now it has shifted to this side. So this has already lost its electron, so it could have positive charge here. And what do we see? This atom is now, it has obtained an extra electron, and that's why it could have a negative charge. And anyway, the net charge of this species would be same during a chemical process, and so the net charge here is zero, so this net charge that is negative and then it is positive. There should be a negative, positive and negative charge here, so net charge will still be zero. Now another, so what we see, the one type of electron movement is pi bond to adjacent bond position. So pi bond to adjacent bond position means the pi bond is shifted to adjacent bond position. So this is one type of electron movement. Another type of electron movement is pi bond moves to the adjacent atom or to the bonded atom. So that this pi bond is moved to this adjacent atom, this bonded atom. So this bonded atom will obtain one extra electron, one electron which was already having with the pairing. So actually a lone pair of electron will appear on this Y and this lone pair because this pi bond has shifted to this atom. So this atom should have two electrons which were part of this bond, and so a lone pair one can represent this as the form of lone pair, and ideally a negative charge here, a positive and a positive charge on this place as well. There will be no positive charge on this place or negative charge. Positive charge will be here and negative charge will be here because the shared pair of electron of this carbon, which is a carbon atom, is now moved to this Y atom. And so this Y atom has obtained an extra electron. One electron of the shared pair was belonging to this atom itself, Y atom. It has obtained only one extra electron, so it will have a negative charge, and this atom has lost its electron because of this movement, so it could have positive charge. We are not focusing on that. So what we are saying that if the shared pair of electron, the pi electron, shifts to this Y atom, so this Y atom should have a lone pair of electrons, and this side of type of electron movement should also understand. Now the third type of electron movement is the movement of electron from adjacent atom to the bond position. And this means this atom to this bond position. So this atom is having a lone pair, and now this lone pair of electrons may move to this atom. And if this is moving to this atom, so what will we have? We'll have this bond will become a double bond, and the lone pair now will vanish from this because now this is no longer a lone pair. It is now, it has become a bond pair, so there is no lone pair of this atom. And so ideally, again, ideally one should have a so a positive charge at this center and negative charge at this center, because this atom, if it is a carbon atom, has accepted an electron, and this Y atom effectively has lost one electron because it has given two electrons in bonding, and its contribution will consider to be, and only one electron is considered to be its part in the shared pair of electrons, and one atom which has given, extra atom which it has given, will now belong to this carbon atom. And so this carbon atom obtain an extra electron than the number of protons it has in its nucleus, so it will be having a negative charge and it will be having a positive charge. And since we are focusing mostly on the movement of electrons here, so we have not shown any positive negative sign. So the lone pair is now shifted to this bond position from this atom Y, and so we see a double bond here and no lone pair at this position. So these are the three types of different types of electron movements that we usually encounter in organic chemistry. So electron displacement effect in covalent bonds. Now let us see. So electron displacement effects, there can be two different types of electron displacement effects as I have said earlier. One is the temporary effect and another is a permanent effect. The permanent effect is because of the bonding, chemical bonding, and the bond nature of the bonded uh, atom or the bonded atoms or the species or the group of moieties, and the temporary effect is because of the reagent or the reaction condition. So the electron displacement in an organic molecule may take place in the ground state either under the influence of an atom or a substituent group or in the presence of an appropriate attacking reagent. The electron displacement due to the influence of an atom or a substituent group present already present in the molecule cause permanent polarization of the bond. So it causes permanent polarization of the bond. And the examples of this permanent polarization of the bond or the polarization of the bond or the displacement of electron density because of the presence of an atom or the substitute group are the inductive effect and the resonance effect. Inductive effect and the resonance effects are they are created because of the electron displacement, that is the permanent effect that is already there in the real molecule, and this is because of the substituents or the atoms that are already present in the molecule. So I'll again read it again. The electron displacement due to the influence of an atom or a substituent group already present in the molecule causes permanent polarization of the bond. Examples of this type of electron displacements are inductive effect and the resonance effect. And what is the inductive effect and what are the things? Those in resonance effect is actually in study, and the inductive effect means the induction. It is caused by, it is induced by certain group, and then the resonance effect that we will see what does it mean later on. Now, then these are the permanent effects. There are also certain temporary effects, and that because of this temporary effect, we also see the electron displacement. And the temporary electron displacement effects are seen in a molecule when a reagent approaches to attack it. And when a reagent approaches to attack electron attack a chemical species, and so what do we see? We see a temporary shifting of the electron pair in a certain direction, or the displacement of electron pair in certain direction. That electron shifting of electron density in a certain direction occurs only when this reagent is there, which causes this effect. Once you remove this reagent, this effect is this effect goes away. So the temporary electron displacement effects are seen in a molecule when reagent approaches to attack it. This type of electron displacement is called electromeric effect or polarizability effect. So the electromeric effect is an example of the temporary electron displacement effect. So if this is the chemical species, and if this chemical species is now influenced by the H plus ion, means if the H plus ion, the acid is added to this ethylene molecule, H plus ion is added to this ethylene molecule. So what will happen? This lone pair of electron will now move to this, so it will take away this H plus ion, and this H plus ion will not go to the both of the bonds. Usually it will shift to one of the carbon atoms, and one of the carbon atoms now it has shifted to C. There is this CH3, this electron density which was between this carbon atom and this carbon atom. Now it has shifted to this carbon and this hydrogen atom. And so what we see, there is plus partial positive, partial negative charge because of the induction. This is positively charged center, and the positively charged center now polarize this center, and because of that we see a negative charge of positive charge generation in this two carbon. Now finally this negative centers will attack, it will combine with this H plus ion, and we will see a positive charge permanent on this carbon atom. So H2C plus charge and then CH3. So this electron density, this lone pair is now shifted between, which was not this pi electron density which was between these two carbon atoms is now shifted between this carbon and this hydrogen atom. So another example is this. This is a carbonyl group, and this carbonyl group can be a nucleophile can attack this electrophilic center. And now, if this is gone here, so what will happen? We'll see the Cn minus ion, it will attack here, therefore partial positive charge here. And now alone this oxygen, this shared pair of electron will now shift from this oxygen atom because it was already having anyway higher electronegativity. So there was already a polarization of this bond because of that. So once this attack happens, so this carbon cannot have more than 4 valency, covalency. And so the theta valency of this carbon must be maintained. So this pi bond, which is a weaker bond, will now break, and this will break, and both the electrons will now shift from this oxygen. So usually what happens, the sigma bonds are stronger, and for a sigma bond, a pi bond can be broken. And so for the sigma bond, a pi bond will be broken. So we see that this electron displacement effect, and this electron displacement effect will be effective only till the Cn minus ions are there into the solution. Once you remove all the Cn ions by any method, what do we see? You will see that this molecule now it will get back to this position. So if by any means if you remove this Cn minus ions, so this is a temporary effect, it will go back. Or this temporary effect is what happens. This is also this will be have an intermediate, and this electron may get back here, and a living group may depart away from the center. And this is what we see usually in nucleophilic substitution reaction. So anyway, now let us see the inductive effect, the permanent effect, and in the permanent effect, let us first focus on the inductive effect. So inductive effect, as its name itself suggests, because of the induction of a certain bond, and this is induced by certain species, certain atom, or the substituent that is permanently bound to a chemical species, means which is permanently well, attached to a chemical species. The covalent bond formed between atoms of different electronegativity, the electron density. So, in a covalent bond formed between atoms of different electronegativity means the atoms are having different electronegativity, and if there is a chemical bond formation between them, the electron density is shifted more towards the atom with higher electronegativity. And this is what we already know. Such a shift of electron density results in polar covalent bonds. And the shifting of the formation of a polar covalent bond or shifting of electron density actually is the real reason behind the inductive effect, because this difference in the electronegativity induces this effect. And so such effects are called inductive effect. So bond polarity leads to various electronic effects in organic molecules, and let us consider this actually leads to various electronic effects, and this electronic effect, because electrons are moving, electron density is moving in certain direction, so such effects are called electronic effects. So this effect is also an electronic effect, because the Cn minus H changes the electronics of this center, and so this center becomes this. This H plus ion changes the electronics of center, and this center has become this. So these effects are actually called the electronic effect. We also see certain effects that is because of the state that we call steric effect, and that effect is because of the steric hinges and the presence of certain atom or group at a particular position. So if it is available at the particular position, so it also causes certain effect. It may not allow other species to come or approach the molecule from that side, and that those effects are called steric effect. Steric effect. So we see usually two kinds of effect. One is called electronic effect, and the other is called steric effect. And all the electronic displacement that we are studying, they are part of the electronic effect. So electron movement in an organic molecule, actually they are part of the electronic effect. The steric effect is associated with the size or the bulkiness of any group that is attached to a carbon atom or that sits beside any species because of any other reason. So let us now consider the example of chloroethane, the CH3CH2Cl, in which CCl bond is a polar covalent bond. So in this species, carbon chlorine bond is a polar covalent bond because of the difference in electronegativity between chlorine and carbon. So it is polarized in such a way that the carbon one gains some positive charge delta plus and chlorine some negative charge. So chlorine is more electronegative. So it gains some negative charge, and the carbon atom to which this chlorine atom is linked, it will acquire certain positive charge, it will gain certain positive charge because the electron density is pulled away from the center towards the chlorine. So in turn, carbon one, the numbering, if you want to do the numbering, this is the chloroethane, and this is the first carbon, this is second carbon, so this is carbon one, this is carbon two. So in turn, carbon one, which has developed a partial positive charge delta plus, draws some electron density towards it from the adjacent carbon-carbon bond. So what do we see? If a positive charge is now appears on this carbon center, this carbon atom carbon one. So because of the appearance of positive charge, what is the effective nuclear charge of this carbon atom will increase, and if the effective nuclear charge of this carbon center is increased, what will it do? It will be now it will now be more than the previous effective nuclear charge of this carbon atom. If this chlorine was before adding this chlorine, so now what do we see? This because of the increase in effective nuclear charge, the shared pair of electron that was between this carbon and this carbon is now shifted towards this carbon because of the presence of this positive charge. So this carbon center also will obtain some partial negative charge, which will be lesser than the partial positive charge. So this will also acquire again some partial positive charge. This partial positive charge, so delta delta plus one can be named. Delta delta plus means this partial positive charge is lesser than this partial in amount. And so in turn carbon 1 which has developed a partial positive charge delta plus draws some electron density towards it from the adjacent carbon-carbon bond. Consequently, some positive charge, the delta delta plus develops on carbon 2 also, where delta delta plus symbolizes a relatively smaller positive charge as compared to that on carbon 1. And this positive charge is lesser than this, and this is because whatever the positive charge is carbon atom has acquired because of the polarization of this bond, and that effect charge will now causes the extra cooling of this shared pair of electrons, and that will not be 100% translated into this cooling, and so this will have this certain process. So what do we see? This becomes delta delta plus charge, and this delta plus center will become delta plus minus delta delta plus. Ideally, it should have this much charge, and that is why the net charge on this molecule should be equal. And what do we see? Usually, after the shifting of this delta delta plus charge from this carbon to this towards this carbon, that is also a polarization. We usually see this carbon center will be having delta plus minus delta delta plus charge, which we have not shown because delta delta plus is very less, and so delta delta plus is major, so one can ignore. Then only if this is delta plus minus delta delta plus, then only the net charge of this entire system is zero, because otherwise, if you see the net charge in this condition is delta minus plus delta plus is zero, and so the entire species is having this fluoroethane plus delta delta plus charge, which is not correct. So usually we should also show that. You should understand this, which it is not necessary to show this delta plus minus delta delta plus. So anyway, consequent to this thing we have already seen. In other words, the polar carbon fluorine, this polar carbon fluorine bond induces polarity in the adjacent bond, and so this polar bond induces polarity in this bond, because this bond has also now become polar. And so this is what such polarization of sigma bond caused by polarization of adjacent sigma bond is called the inductive effect. So this polarization of this sigma bond because of the polarization that is already created due to difference in electronegativity in this bond is called the inductive effect. So this inductive effect is passed on the subsequent bond as you see. So for this bond is more polar, and this also passes to the next bond and to the next well, but usually after the third bond it becomes negligibly small. So this effect is passed on the subsequent bonds but decreases rapidly as the number of intervening bonds increases and becomes vanishingly small after three bonds. So after the third bond it becomes negligible. Although it passes through the sigma bonds to along the carbon chain of any organic species, but after the third bond it becomes almost negligible. The inductive effect is related to the ability of substituents to either withdraw or donate electron density to a attached carbon atom, and so what we see, the inductive effect that is created here is because of the ability of this chlorine atom to withdraw electron from this carbon center. So because it is more electronegative, having higher effective nuclear charge, so it can withdraw electron shared pair of electrons from this carbon to towards itself, and subsequently from this carbon to this carbon as well. So this electron withdrawing tendency causes this effect. Similarly, there are species as well which causes electron donation effect, and so that we also call the electron donation tendency, or those species are called electron donating group, and this species which withdraw electrons are called electron withdrawing group. So the inductive effect is related to the ability of substituent. So this is a substituent on to either withdraw, means the pooling, or donate electron density, means the donating, the giving electron density to the attached carbon atom, to this attached carbon atom. Based on this ability, the substituents can be classified as electron withdrawing group or electron donating group. If the substituent withdraw electron density, it pulls electron density, then such substituents are called electron withdrawing substituent or electron withdrawing group. And if the substituent or the group attached to a carbon atom donated electron density to the carbon atom, such substituents or the groups are called electron donating groups or electron donating substituents. So halogens and many other groups as we have seen here, which are having very high electron density, which are non-metal, are with non-metal very highly electronegative elements. So they causes, and along with this halogens, there are many other groups as well, like NO2, cyano. These are groups; they are not atoms, so they can be subsequent of the group. Cyano group C triple bond N, carboxy group C double bond OH, ester group COOR group, aryl oxy group or alkoxy group as well, aryl oxy group, etc. are electron withdrawing groups. Not only these groups are the electron withdrawing groups, but we also know the electronegativity of carbon increases when S character of the carbon increases. Means the S character means the carbon is sp hybridized, like that we see in the acetylene. So the electronegativity of the carbon atom also increases. So if C triple bond C H group is attached to a carbon atom, then this group, the C triple bond CH, also because of its higher electron density, higher S character, behave as electron withdrawing group. Similarly, C double bond C can also behave as electron withdrawing group, and thus the benzene rings which are having three triple bonds, they are also electron withdrawing group. So benzene rings in the form of substituents are called phenyl rings, and so the phenyl rings C6H5 is also electron withdrawing group or electron withdrawing substituent. So there are many electron withdrawing substituents. This electron withdrawing substituents you can easily understand, because you know there is a heteroatom, carbon heteroatom bond, and here nitrogen oxygen bond. So nitrogen is having higher electronegativity than carbon, and now this nitrogen, the electronegativity is further increased because it is attached to two oxygen atoms, which is which are having higher electronegativity than even nitrogen atom. So this entire group is behaves as a very strong electron withdrawal. Similarly, CN group is a strong electron withdrawing group. If NH3 plus group is attached anywhere, like ammonium, that group also behaves as a strong electron withdrawing group. The carboxylic acid group, carboxyl group. This carboxyl group C double bond O then O. Two carbon oxygen bonds, and the carbon oxygen of bonds are polar bonds, and these polar bonds actually causes the polarization of the carbon carbon bonds, and because of that polarization of carbon carbon bonds, the inductive effect is created. So this also induces electron withdrawing effect of the polarity in the carbon carbon bond. So this is also the tenth. We see the esters with a similar analogy one can draw with the carboxyl group. Then the aryl alkoxy. Aryl alkoxy is aryl group and oxygen. Like phenyl group, you see example. Phenyl group is attached to an oxygen atom. Like phenol. If you remove hydrogen atom, the hydrogen atom from this phenol, you will get the aryl alkoxy, or this is the phenoxy group. This phenyl and this oxygen is phenoxy group. Similarly, the alkoxy group, like aryl oxy group, we can have this group, alkyl group, like CH3O. These CH3 groups are also electron withdrawing groups. And then again, as I said earlier, C triple bond CH group is also electron withdrawing group. Benzene phenyl group is also electron withdrawing group because of the presence of double bond. Acid, this Alkenes, the alkene group double bond C double bond CH2, CH double bond CH2. This group is also that this group is called vinyl group. CH double bond CH2 is called vinyl group. This vinyl group is also an electron withdrawing group. Although this electron withdrawing effect of this group is very weak, but this group will also behave as an electron withdrawing group. On the other hand, alkyl groups like methyl, ethyl, etc. are usually considered as electron donating groups. And the electron donating groups, how the electron donating effect is created in this when this species or these moieties are present to a carbon atom or to any bond that we will see later on in the terms of hyperconjugation, but this is already there. So the alkyl groups are electron, they behave as electron donating groups. The electron donating effect of alkyl groups follow the order. This order, the tertiary alkyl group is having highest electron donating tendency, then secondary alkyl group, then primary alkyl group, then methyl group. So that this order is what tertiary butyl, then secondary butyl, then iso. Example, if you see, then isobutyl, then n-butyl. What is tertiary butyl? The carbon atom is attached to three methyl group and one side which will be attached to the carbon chain. So tertiary butyl group, carbon, and then one me group methyl, another methyl group this side, another methyl group this side, and one bond that can be here. It can be linked to a carbon chain or the main chain. The secondary butyl group, this means the secondary carbon atom is, so this is suppose one, two, three, and and another group is present. So this is secondary carbon atom is here. The secondary butyl group can be here like if this. If this part, this entire group is attached to the carbon chain with the second carbon atom, then it is called a secondary butyl group, and secondary butyl group will have two substituents, one methyl and one ethyl, and so the secondary butyl will be having higher. Then isobutyl group. Isobutyl group will be what? Like this group and this group. If this is what? If this atom is one of the any terminal atom, if this one is this isobutyl group is connected to the main chain or the main chain hydrocarbon. So what does it mean? Isobutyl group. Earlier I have already shown what could be the isobutyl group. We don't want to go that much that back. So what is the isobutyl group? One can understand is sorry, this is what is propyl group, and then one can have this group, and if this group is now attached to this carbon atom is attached to this, so this entire group is called the isobutyl group. So what do we see? This carbon atom, although this is having branch at the second carbon atom here, but this is only the primary hydrocarbon. The primary will behave as a primary alkyl group. And then the N-butyl group. If this is the butyl group, and if the carbon atom is now linked to the main chain, this is called the N-butyl group. So the but electron donation tendency one can such is highest for tertiary butyl, then secondary butyl, then isobutyl. N-butyl is usually tertiary alkyl, then secondary alkyl, then primary alkyl, then methyl alkyl. So let us now see some questions. So which bond is more polar in the following pair of molecules? So we have to find which bond is more polar in this species. So what do we see? This is CH bond, and here it is CBr bond. So both bromine is having higher electronegativity than carbon, but in the carbon and hydrogen, the carbon is more electric than electronegative than hydrogen. And another thing is to find out the polarity of the bond. We also see the dipole moment or the bond moment of this bond, and the bond moment of this bond will be much larger than this because this atom is also larger, and also this is having higher electronegativity and higher electronegativity. So we see a larger separation of electron between these two atoms and this between C and H. So that the CBr bond is more polar. So which bond is more polar in the following pair of molecules? In this pair of molecules, this CBr bond is more polar since bromine is more electronegative than hydrogen. Then in the next question, the CNH2 bond is the CN bond and COH bond. So this carbon between carbon and oxygen or carbon bond, and its carbon nitrogen bond. Between nitrogen and oxygen, if you compare electronegativity, oxygen is more electronegative, so the C4 bond will be more polar than CN bond. So the CO bond, again the what we see, the higher difference in electronegativity between carbon and oxygen, so the carbon oxygen then the carbon sulfur, and so the carbon oxygen bond one may consider as the more polar bond. Now let us see the next question. In which carbon-carbon bond of CH3, CH2, CH2Br, the inductive effect is expected to be least? So there are two carbon-carbon bonds. This carbon 1, carbon 2, carbon 3. So carbon 1, carbon 2, and carbon 2 and carbon 3. So this carbon 1 and carbon 2 bond is closer to bromine, and as we know the inductive effect is translated along the chain, but its effects diminishes as we go away from the center of the origin. So from bromine, as we go away, as we go further, what will the inductive effect will decrease, and so this bond will be having higher inductive effect and more will be more induced than this carbon-carbon bond. So the magnitude of inductive effect diminishes with distance from the point of its origin is what we know. Hence the effect is least in the bond between carbon 3 and carbon 2. Between this bond and this bond, this effect will be least. And there will be highest of there are only two bonds, so it will be higher on this carbon 1 and carbon 2 bond. Let us now see the inductive effect on acidity and basicity, and we also see the inductive effect, the causes of inductive effect on nucleophilicity and electrophilicity. So, inductive effect on acidity and basicity. The electron withdrawing group, so what we have seen inductive effect is because of the electron withdrawing or electron donating effects of already added substituent to an organic molecule. So the electron withdrawing group increases the acidity we know of a compound due to minus I effect. And why it affects, this is what we should remember. The electron, if an electron withdrawing group is attached to a carbon center or any acid, so its acidity will increase because electron withdrawing group increases the polarity of the X bond, the high bond that is actually where from where the proton has to be liberated. That bond, the H and that X bond becomes more polar because of the minus I effect of electron withdrawing substituent. And whereas it decreases the basicity of the compound by the same effect, an electron withdrawing group, since it decreases the electron density, um, the atom it is attached, so it will decrease the electron density, so it will decrease the basicity as well. In contrast to what we have seen here, the electron donating group decreases the acidity of a compound. So electron donating effect, if you see, it will decrease the acidity of the compound. And why acidity? Because it will increase the electron density of the atom which is attached to the proton. And if it increases the electron density at that atom, so that it will decrease the polarity of the that particular bond, which is that particular bond, and so it decreases the uh, acidity. Electron donating group decreases the acidity of a compound due to plus I effect, whereas it decreases the basicity, whereas it increases the basicity, whereas it increases the basicity of a compound due to the same effect. But it increases the basicity of the compound because it has increased the electron density, and because electron density has increased, now the lone pair is more easily available because of the increase in electron density, and so the electron donating effect increases the basicity. So electron withdrawing substituent attached to an acid decreases the acidity, sorry, increases the acidity. I'm making mistake. So electron withdrawing substituents attached to an acid increases the acidity of that acid. And if the electron withdrawing substituent is attached to a base, it will decrease the basicity of that base. And now that the electron donating species or substituent is attached to an acid, it decreases the acidity of that acid. And if the electron donating substituent is attached to a base, it will increase the electron density and thus the basicity of that base. And this is because the conjugate base of the acid is stabilized via delocalization of the formed negative charge by minus I effect. This is one thing. Electron density, what we see after that, once the proton is liberated, we see the formation of a conjugate base. And now this conjugate base, if the electron density of this conjugate base is decreased, if somehow this electron density that is accumulated on one atom, if it dispersed to some other atoms as well. So stability increases. This is what we have already seen. We already know the electron density dispersal increases the stability of a group, or the charge dispersal, not only electron density, any charge dispersal, positive charge or negative charge. If it is dispersed over many atoms, so the system will become more stable than if it is accumulated at only one atom, because species with a charge on it are not very stable. Charge conditions are not a stable condition. And this is because again, I'll read the conjugate base of acid is stabilized via delocalization of the formed negative charge by the minus I effect, and it is destabilized by electron donating effect of plus I group. And so this the same conjugate base with having negative charge will be destabilized if electron donating group is attached to it, because electron donating group will cause plus I effect. It will push electron density towards it. So it will further accumulate electron density, it will not disperse electron density. And so the stability of the conjugate base will decrease, and if the stability of the conjugate base decreases, the acidity will subtract. If the stability of conjugate base decreases, so the acidity will decrease. Of the acidity of the corresponding acid will decrease. And this is how one sees. This is a carboxylate ion, a negative charge is there, and this carboxylate ion, what happens if an electron withdrawing group is attached to this carbon, so what it will do, it will pull away electron density which was on this carbon, and we see a negative charge already there. So because it pulls away electron density from here, so the negative charge on this carbon atom is dispersed over a longer space, and so it will become stabilized. So electron withdrawing group stabilizes the carboxylate ion in this case. So it's just one example. Now, if an electron donating group is attached to this, means the group is having plus I effect, which can cause plus I effect if it is attached. So what happens? It will push electron density towards the carbon. It will put electron in this direction, and so the electron density at this carbon will accumulate. It will increase, and if electron density increases or the charge density increases, the stability of this group will decrease. So electron donating group destabilizes the carboxylate ions. This is just one example we have seen. Another example one can see as the formic acid is more acidic than acetic acid due to plus I effect of the methyl group in later. So the formic acid, the structure of formic acid is HCOOH. This is formic acid, and the acetic acid is CH3COOH. So the difference only is here in this formic acid we have hydrogen, and in the acetic acid in place of hydrogen we have methyl group CH3 group. But what do we know? Methyl group is having higher electron tendency. As this is with respect to hydrogen. The hydrogen is the reference point for the electron donating and electron withdrawing effect, that is whatever we consider, and that is why what we so we do not show any kind of shifting with this hydrogen. And so this electron with because of this electron donating effect, what happens? The conjugate base of this acetate ion will be less stabilized, and so this acid will become weaker acid. And if this is comparatively more stabilized conjugate base of the formic acid, the formate ion will be more stabilized because it doesn't have anyone to push electron density towards the carbon atom. And so this is a stronger acid than this. Now let us see another example. Trichloroacetic acid is more acidic than di and monochloroacetic acid, or di and mono substituents. And this is why, let us see this. So this is the acetic acid. C, sorry, there should be only C. There should not be CH. Uh, at this center. So there is a mistake. Let me correct it. cannot have. So yes, let us now see this example. One cannot have this. See, look here. This there will be only carbon atom here. So three, all the three hydrogen atoms of the acetic acid CH3 here replaced by chlorine atom. So this is trichloroacetic acid or the tri substitution, chloro substitution is here. So the three chlorine atoms which will pull away electron density from this carbon atom, and because of these three chlorine atoms, this carbon atom will now be significantly electron deficient. Once it becomes significantly electron deficient, it will pull away electron density from this carbon-carbon bond. So this alone shared pair of electron will now shift towards this carbon atom. And now once this is shifted towards the carbon atom, so what we see this carbon atom will again having some positive charge. And because of that positive charge, what do we see? This conjugate base, which is having a negative charge, will be more stabilized. So if you consider the conjugate base of this acid, this entire acid, the conjugate base which is having a negative charge over here, this negative charge will be more stabilized because of the three electron which is going in substituent that is there at this carbon center, because they will pull away electron density, more electron density will be pulled away from the oxygen atoms anywhere and which are attached to this carbon. And so the stability of the conjugate base will increase and so the acidity will increase. That with the stability of the conjugate base acidity increases, this is what we know. So now if there are only two chloro substituents, like in this example, there is a dichloroacetic acid. The dichloroacetic acid, only two chlorine atoms are there to pull away electron density from the corresponding conjugate base. So it will comparatively pull away lesser electron density negative charge comparative to the trichloro substitute dichloroacetic acetate ion. And so this acetate ion, the dichloroacetate ion, is less stable than the dichloroacetate ion, and so the dichloroacetic acid is a weaker acid than the trichloroacetic acid. Now in the monochloroacetic acid, there is only one chlorine atom which can pull away electron density from the conjugate base, and so this will further be weaker. This entire acid is a further be a weaker acid than even the dichloroacetic acid. And this one again one can understand with the stability of the conjugate base, which we have already seen with the structure in this case. You just have to imagine this electron withdrawing group, which is what this is the carbon and this CCl3 group. At this place, the CCl3 group, in this case it is CHCl2 group, CWG, and in this case it is CH2Cl group. So, and as the Cl group, the electron withdrawing groups are increasing, so the stability of the conjugate base will be increasing, and so the acidity will be increasing in this direction. So, this is the strongest acid than this one. Now, the order of stability of ions, if you look at the order of stability of ions, these ions, if you will see, this is the electronegativity of chlorine is more than the chlorine in the monosubstituted haloacetic acid. The monosubstituted haloacetic acid, the conjugate bases we have just shown here, and the fluorine is having highest electronegativity, and so it will pull away maximum electron density from this oxygen atom. So the more charge dispersal will happen in this case than the monochloro substitution. And if chlorine is having high electronegativity than fluorine, and so a more electron charge dispersal will happen in this case than this, and this will in this case more electron charge dispersal will happen than this. And so what do we see? The order of stability of these ions will be this. The fluoro substituted or the fluoro acetate ion. It will be more stable than fluoroacetate ion. The fluoroacetate ion will be more stable than bromoacetate ion, and the bromoacetate ion will be more stable than iodoacetate ion. So fluoroacetic acid is strongest acid, then will come the fluoroacetic acid, then the bromoacetic acid, then the iodoacetic acid. Order of basicity of conjugate bases one can also see. The order of basicity of conjugate bases of acetic acid is example we have already seen. Order of basicity will be in this. Order of basicity again we can see. For this, this should be the order because the electron density is least in this case. The electron density at this oxygen will be least in this case because of the higher electronegativity of this. So the order of basicity will follow this step. Because this will be more basic than this one, then this one, then this one. But this one will be less stable and this one will be highest stable. Yes. So this one is least stable because it is highly basic, more basic. If it is more basic, so it will be less stable in this condition. It will prefer to extract H plus ion and get back to the acidic form. And then this one electron density is least here on the oxygen atom, so this will not prefer to extract H plus ion as much as this group do, and so this is the weakest base, and thus the corresponding acid will be the strongest base. Now the order of basicity of amines one can also see the order of basicity of amines because of the electron donating effect or electron donating use. The secondary amine is more basic than primary, and the primary amine is more basic than ammonia. So usually what we see that because electron donating group increases the electron density of nitrogen, and so the two secondary amine means two nitrogen, it should follow this trend, the secondary amine, primary amine, and then tertiary amine as well. So the secondary amine is more basic than primary amine, that is more basic than ammonia. In the case of tertiary amine, one cannot write tertiary amine here in the same chain because there are certain other factors which also play certain role, and because of that, tertiary secondary amine becomes more basic than the primary amine. And what is that reason? We will study those reasons when we will study the basicity of amines in some other chapters. Just to get the idea of electron withdrawing effect and electron donating effect, I have given these examples here. In details how the basicity of the amines changes with the addition of different alkyl groups or different substituents. Those things we will see in details later on. Now, as we see the basic character, basicity order, one can also define based on the inductive effect or electron withdrawing effect or electron donating effect. Similarly, one can also find details about the nucleophilic effect or nucleophilicity, because nucleophilicity is also the basicity, because basic character electron density, usually if the electron density increases, the nucleophilicity also increases if the nucleophilic atoms are same. And the examples anyway we have seen here earlier, when we have seen earlier in this case. If the nucleophilic atoms are same, the electron density is more, the more is the nucleophilicity. And so the nucleophilicity decreases while electrophilicity increases when an electron withdrawing group is attached to the nucleophile. So when an electron withdrawing group is attached to a nucleophile, it will pull away electron density from the nucleophile, and so the electron density of the nucleophile will decrease at the nucleophilic center or the nucleophilic atom, and so the nucleophilicity will decrease. Nucleophilicity of that atom will decrease. However, the electrophilicity of an atom increases. So if an electrophile is there and if you add electron withdrawing group to add, so the electron withdrawing group will further increases the electron deficiency to that atom. It will pull away electron density. So the electron deficiency will be intensified, and so the electron withdrawing group increases the electrophilicity of a group to which it is attached. In contrast, nucleophilicity increases while electrophilicity decreases when an electron withdrawing electron donating group, this is electron donating group is attached to the nucleophile. So if the electron donating group is attached to the nucleophile, the electron density at the nucleophilic center will increase, and so the nucleophilic character will increase, but the electrophilic character will decrease because electron donating group, if it is attached to an electrophilic center, it will push certain electron density towards that center, and so it will decrease the electron deficiency, or it will diminish the electron deficiency of the electrophilic atom, and so the electrophilicity will decrease in that case. Then the next effect is the resonance effect, and this resonance effect we will study in our next class. Before the resonance effect, we will see study about the resonance structure. What does the resonance structure mean? And once we understand the resonance structure, we will be able to also understand the resonance effect of the R effect, which we also call the R effect, or the resonance effect is also called the mesomeric effect or the M effect. Like what we have seen, minus I effect and plus I effect. Minus I effect is electron withdrawing effect, and plus I effect is electron donating effect. Similarly, we also see electron withdrawing effect in resonance and electron donating effect in resonance, and those effects are generally minus R effect and plus R effect. Minus R effect is electron withdrawing effect of resonance, and because of resonance, and plus R effect is electron donating effect because of the resonance, and since these effects are also considered called as mesomeric effect, so one can analogously say minus M effect and plus M effect. Minus M effect, electron withdrawing effect, and plus M effect, electron donating effect. So what are the rules, other things in details we will study in our next lecture. So for now I will stop here.